Here are the answers to the L'Hopital's rule exercises. And there are 6 examples that you have to work out, and then 4 multiple choice. And number 6 and 7 through 10 are on the page that talks about the indeterminate forms. Okay, so I'm going to go over the answers in more detail if you need, and feel free to jump ahead to what you need to look at. So I think we looked at example 1 and 2 when we were meeting the other day. So I'm going to start with example 3. Okay, so with example 3, the first thing I want to do is I want to check what the limit is as x goes to infinity. So the limit of the natural log of x as x goes to infinity is infinity. Remember, the natural log graph looks like this. So y is going to infinity even though it's going very slowly. All right, and the cube root of x, that graph looks like this. So it is also going to infinity. So we have infinity over infinity. All right, so we're going to apply L'Hopital's rule, which means we're going to take the limit as x approaches infinity of the derivative of the derivative of the natural log of x over the derivative of x to the 1/3. So that's 1/3 x to the negative 2/3. Let's do a little algebraic simplification. So this is really 1 over 3x to the 2/3 in the denominator. And so when you divide fractions by fractions, you take the reciprocal and multiply. So this is going to turn out to be x to the 2/3 divided by x. All right, simplifying a little bit more. That's 3 over x to the 1/3. This time, as x goes to infinity, 3 divided by x to the 1/3 is going to approach 0. And there you go. That's the answer. All right, moving along. Example 4, find the limit as x approaches 0 of tan of x minus x over x cubed. Let's check what that limit actually is. If x becomes 0, the tangent of 0 is 0 minus 0 over 0 cubed. So we get 0 over 0. That means this limit is a candidate for the L'Hopital's rule. So we're going to take the limit as x approaches 0. The derivative of tangent is secant squared of x. Derivative of x is 1 over 3x squared. Okay, now here it might be helpful if we remember what is the secant squared minus x. So you remember that cosine squared x plus sine squared x equals 1. If I divided every one of these terms by cosine squared, I would get 1 plus tangent squared x equals secant squared x. So that was dividing by cosine squared. All right, so therefore tangent squared x is secant squared x minus 1. So I'm going to rewrite this ratio as the limit as x approaches 0 of tangent squared x over 3x squared. All right, we're going to evaluate the limit again. The tangent of 0 is 0. The tangent of the evaluating 3x squared at 0 is also 0. Okay, so this means we're going to do L'Hopital's rule one more time, or as many times as we need, but maybe one more time will be it. So the derivative of tangent squared x, remember that's tangent of x quantity squared, so we have to do the chain rule. So that's going to be 2 tangent of x to the first power times the secant squared of x. The derivative of 3x squared is 6x. Okay, already I can see this is 0 over 0 again, because we're going to have the tangent of 0 and 6 times 0. Okay, so we've got to go one more time maybe. All right. Let's reduce first and get a 3x down here. And I'm just trying to think if we could simplify the numerator at all. We could call this secant squared 1 plus tangent squared x, and then not have to do the product rule. So let me just say I'm not going to do L'Hopital's just yet. I'm going to clean up this algebraic work here and call this tangent of x plus tangent cubed of x over 3x. All right, so now I don't have to do the product rule. I can just do the chain rule where I need to. So the limit as x approaches 0 of secant squared of x plus 3 tangent squared of x times secant of x, secant squared of x over 3. Okay, so it's looking better in the denominator. And in the numerator, I need to remember what is the secant of 0. So remember, secant is 1 over cosine. So secant of 0 will be the same as 1 over the cosine of 0. And the cosine of 0 is 1. So secant 0 is 1. So I'm just checking if I take the limit now. So we are going to get 1 plus 0 over 3. So I think the answer is 1/3. That one definitely took more work, doable, and very helpful if you remember your trig. Okay, number 5, the limit as x approaches 0 of sine of x minus x over x cubed. Let me check what happens when I evaluate. Sine of 0 is 0 minus 0 over 0. So 0 over 0 is a candidate for L'Hopital's rule. Derivative of sine is cosine of x. Okay, so I get cosine of x minus 1 over 3x squared. Letting x go to 0, we're going to get 1 minus 1 minus 1 over 0, which is 0 over 0. Let's apply L'Hopital's rule again. The limit as x approaches 0, negative sine of x over 6x. Okay, that's going to be 0 over 0 again, so let's apply L'Hopital's again. We're going to get negative cosine of x over 6. Letting x go to 0 gives us negative 1 over 6. Okay. All right, so there are 5 indeterminate forms. Infinity minus infinity, 0 times infinity, 1 to the infinity, 0 to the 0, or infinity to the 0. And we can talk about why these are indeterminate when we meet again. But in order to determine the limits, each of these indeterminate forms must be transformed into a 0 over 0 or an infinity over infinity. So that's what I need to see in order to apply L'Hopital's rule. All right, so in the case of infinity minus infinity, that might be like a fraction minus a fraction. Let's get a common denominator. In the other forms, try to rearrange the fraction. So for example, or rearrange the expression into a fraction. So for example, x e to the negative x, we can move that negative exponent down to the denominator. Okay, example number 6. The limit as x approaches 1 from the right. Okay, well, and why do you think they did from the right? Because here we're doing the limit of 1 over the natural log of x, or negative natural log of x, 1 over negative natural log of x. So anyway, just thinking about the natural log of x graph, its limit is only defined from the right-hand side. Okay, so we can't do a limit on the left. Oh, wait. No, I apologize. I was thinking at x equals 0. We're actually doing it as x equals positive 1 from the right. So actually, we're just taking a look at this as x approaches 1 from the right. So the answer would be 1 over 0. Okay, so we're going to get 1 over 0 minus 1 over 0. Okay, this in fact is indeterminate, right, for that reason, because we'd think of 1 over 0, 1 over something getting very close to 0 as infinite. Okay, so using the common denominator strategy, let's get a common denominator. So the denominator would be x minus 1 times the natural log of x. The first numerator will be x, the natural log of x. The second will be negative 1 times x minus 1. Right, there's a room for a lot of error if you forget that you're going to distribute that negative 1. Okay, so right now I can see that we're going to get 0 over 0, so we can apply L'Hopital's rule. Okay, so the derivative of the numerator. I'm going to have to use the product rule. So x times 1 over x plus natural log of x times 1 minus 1. The derivative of all of this is just negative 1 over the derivative of the denominator. I'm going to have to use L'Hopital's rule, the product rule again. So that's going to be x minus 1 times 1 over x plus natural log of x times 1. Okay, before we go further, let's do a little algebra to simplify this mess, because I've got complex fractions. Well, this guy can cancel out and become 1. And so I have in the numerator 1 minus 1. So these guys are going to drop out. So I'm just going to have the natural log of x over 1 minus 1 over x. Actually, I'm going to leave that. I'm going to take this a different direction here. I'm going to do x minus 1 plus natural log of x plus x times the natural log of x, getting the common denominator. And then I have a natural log of x divided by this fraction. Why don't I take that denominator and move it up to the numerator as if I multiplied by the reciprocal, right? So I'm just going to put that x in the numerator. Okay, let's check. As x approaches 1, we're going to get 1 times 0 over 0 plus 0. So we're still at 0 over 0. So let's apply L'Hopital's again. Okay, x times 1 over x is going to be 1 plus the natural log of x. That's the product rule on the numerator. Derivative here